So what I'm going to tell you today is about some of the recent results we had about ion accelerations, mostly driven by Petawatt femtosecond laser pulses. So before I start, I would like to acknowledge my collaborators who were mostly part of this campaign, mostly in experiments, in theory, and in numerical simulations. So here is the brief outline of the talk that I'm going to tell you today. So we'll have a brief introduction about the center, the CoReLS center where this laser is. And then we are going through a series of topics which are related to intense laser matter interactions. And then we will summarize the talk. To begin with, the Center for Relativistic Laser Science is a center which is dedicated to explore basic research driven by ultra-intense, ultra-short laser pulse interactions. This center is in the Gwangju city of South Korea, which is also known as City of Light, very well appropriate for intense lasers. The features of this center is that we have dual petawatt facilities there. So we have 2 petawatt arms, namely 1 petawatt and 4 petawatt. And with these lasers, we can do, and we do a variety of experiments, namely high densities, where we are shooting micrometer thick or nanometer thin foils, or we do underdense plasma experiments, mostly by accelerating electrons to GeV energies. And recently we have started near critical density experiments, which is dedicated mostly towards laboratory astrophysics and phenomena. But today's talk will be mostly dedicated towards high density experiments, which is interaction of laser with thin foils. So before I proceed, here are some glimpses or the parameters of the lasers that we use. So the peak power is something like 1.5 petawatt, and the pulse that we use can be compressed down to roughly 30 femtoseconds. And one very crucial parameter that we have to worry about is the contrast of the laser. By contrast, I mean the ratio of the peak pulse and the pedestal. So the contrast that we have is roughly 10 to the minus 10 till hundreds of picoseconds. And we can improve it further by using plasma mirror, but in most of the experiments, this contrast is good enough. And other parameters which is crucial here is the focusability of the beam, how tightly we can focus the beam. So in this case, without using wavefront corrections, we can go down to 5 micron. And the peak intensity that we achieve is roughly 10 to the 21 watt per centimeter square. So this is enormous intensities that we can achieve at the target front, and with which we can do truly relativistic physics. So, but there are challenges like in any other experiments, and the challenges that we face here is whenever we shoot a thin foil, we get enormous amount of back reflections in our beam lines. And these back reflection comes even if we are shooting at oblique incidence, which is non-normal incidence. And this is shown here in the first schematic figure here. So if we send a laser through our beam lines and then focus it down on a target, a surface of a target at non-zero incidence, we get something like 1% of the back reflections, which goes back to the beam line. Now 1% is a very small number, but imagine that if the laser itself is tens of joule, then the back reflection can be something like order of millijoule. And this can cause serious damage in the beam line like optics or the gratings. So this is something that we have to worry a lot when we are doing this high density plasma experiments. And to understand this, actually we carried out a series of simulations and experiments. So the bottom left figure that we are seeing is telling us how, when we change the intensity, how the back reflection actually increases. So we see that it can change like orders of magnitude, when we are changing the intensity from 10 to the 18 all the way till 10 to the 20. So there's an enormous amount of back reflection which is coupled with the laser intensity. The second figure that we have on the right-hand side, it tells us how, if you change the angle of incidence, for example, if you go to very large angle of incidence, like 30 degree or 40 degree, we see that the back reflection actually goes down, which makes sense because we are going away from the normal incidence. But interestingly, we also have a pre-plasma scale length scan. So the red points that you see is of the 0 plasma scale length, and the black triangle that you see has a certain pre-plasma scale length associated with this. So whenever we add a bit of pre-plasma, it actually helps to reduce the amount of back reflections we have, which is in a sense very helpful to avoid the damages from the back reflection. And to understand this more, we did a 2D peak simulation, which is shown here. So here we have, on the top, we have a target, which is roughly 2 micrometer thick. And then we have incident laser pulse coming at 30 degree. And then what we are trying to see is how does the electron density profile changes as a function of time. So here we have 3 figures, figure A, B, and C, which are indicated at 3 different times, like 5 femtoseconds, 21, and 32 femtoseconds. The first thing that we notice is there is a strong modulations happening at the front of the surface. So these are all electron density profiles. So as the laser interacts with the surface, the electron density profile is no longer smooth. It is very rough, very inhomogeneous, and we cannot define a plane of incidence in this case. Because of this roughness, we get a huge amount of back reflection. So whenever we have a strong modulations in the electron density profile, it is inevitable to avoid any back reflections coming from the surface. So this is very fundamental feature of laser plasma experiments, and this is something we have to worry in futures when we are scaling up the laser intensities for this kind of experiments. So the next topic that we would like to discuss is calibration of detectors for energetic particles. So as the laser intensity goes up higher and higher, the particle energy which are accelerated by this field, they're also bound to go up. But the question is, do we really know the response of our real-time detectors about these high energy particles? So that is the question we're trying to answer. So which is shown here in the schematic here. So we have a target which is exposed or irradiated by the laser field, and the accelerated particles actually, they are captured by a Thomson parabola spectrometer. And one of the good real-time detector is microchannel plate. So the idea is to calibrate microchannel plate, a response of this plate towards the energetic particles, namely proton or carbons. So to do that, we actually use a CR39 plate, a plastic nuclear stack detector. And the beauty of this is, CR39 is that we can absolutely count the number of particles by some chemical etching. And what we are showing you is 2 figures. On the left side, we see the trace of CR39. And on the right side, we have a microchannel plate, which is real-time diagnostics. And using CR39, we can actually get the absolute calibration of MCP for any number of particles like protons, carbon, or oxygens. So the results are shown in the next slide here. So on the left-hand side, we have a carbon ions, and on the right-hand side, we have protons. For carbon ions, we have actually multiple species. We have carbon 4+, we have carbon 5+, and also 6+. And what we see is the response of MCP is not very sensitive towards the charge of the ions involved in the experiment. They are broadly similar. So there is not much charge dependency, although there is an energy dependency. So there's optimum energy response of MCP towards certain species. When we go to the protons curve, this is also very interesting. So up to, let's say, 10 MeV, we see a very flat response of the detector. But after that, actually response goes down, which is shown by the red points here. Now this happens because our detector is transparent to protons having more than 10 MeV energy. So if we launch protons more than 10 MeV, they are not actually stopped by the detector. They just pass by. But while passing by, they deposit a fraction of their energy, which goes into response of the system. Now, the question is, so till 20 MeV, we have seen a response, a non-zero response in the medium. But what if the proton energy is boosted to 100 MeV, which is the future aim? So this is the answer we would like to seek in the future, where proton energy is so high that it deposits nearly negligible amount of energy in the system. So that is something we have to worry about future. Moving on to the next section, it's also an interesting topic, which is about getting the intensity scaling of ion acceleration, especially in the femtosecond petawatt regime. So we would like to know, if we are at certain intensity level, what is the kind of energies that we are getting? And if we simply scale up this intensity, what would be the response of the ions? How would they scale with respect to the laser intensity? So to do this, we again carried out very simple basic experiments where we are irradiating roughly few micron thick metal foils by oblique incidence laser pulse. And we are measuring ions on both sides of the target, namely forward side and the backward side. And the raw traces of the ions, the parabolic traces of ion, is shown on the top right and top left side. So we have multiple species. We have protons, we have carbons, we have oxygens. But let's pick one of them, let's say proton, and then try to study how does the proton maximum energy changes with laser intensity. So this is the scaling we have shown on the next slide here. So on the left side, we have forward proton scaling, and on the right-hand side, we have backward proton scaling. And as we see that on increasing the laser intensity by 1 order of magnitude, we see that the proton energy goes up drastically. And we can fit a power law, which shows that the I to the power 0.75 fits very well on the forward side. Whereas on the backward side, it goes something like I to the power 0.5. So the forward scaling, which is towards the laser axis, has much faster response as compared to the backward direction, which is away from the laser axis. So this is something interesting that we found out in this campaign, that even on the backward side, we have significantly high energy of protons coming out, which was not the case some times ago. So the next section is about modulating an ion spectrum. So the typical spectrums that we have, they are very Maxwellian-like, but for certain purposes, we do require modulated or quasi-monogetic ion spectra, and there are various ways to do this. But one very basic scheme which can deliver this target is by using multiple species of ion accelerations. So what I mean by that is that if you simply irradiate a thin foil with high power lasers, we can get multiple traces of ions, namely hydrogen, carbon, oxygen, or even heavy element. But these are all very plain spectra. There is no quasi-monogetic feature here. But in some cases, if you look carefully, at the tail of the spectra, at the high end of the spectra, there is a slight modulations appearing in both oxygen, carbon, and the proton. And it can be seen more clearly if we draw a constant velocity line from the 0 point, which is shown by the line here. So the dashed line that we have is a constant velocity line. It indicates that all the modulated part belongs to the same velocity. So to quantify this, we can plot actually spectrums, and this is what we have shown here. So these are all kinetic energy spectra of different ions, namely the green curve is for hydrogen, the gray and the red curves, they are for carbon 5+ and 6+, and the blue curve is for the oxygen. Now, if we start with the proton curve, which is the green curve, we see that there's a prominent dip at certain energy or certain energy per nucleon. And there is also a modulated features in the carbon. So for example, carbon 5 plus and 6 plus has a bump at the same velocity region where the proton has a dip. Similarly, where the carbon has a modulation, there is a maximum velocity front of the oxygen. So in a sense, maximum velocity of the carbon ion is same as that of the proton, and maximum velocity of the oxygen ion is same as that of the carbon. So we can say that the carbon is actually modulating hydrogen ion, and oxygen is modulating carbon ions. So the heavier element is actually modulating that of the lower mass element. Now this is something was shown by Foucault in very beautiful 3D PIC simulations. There he simulated multi-species expansion of plasma. And the top right figure that we see is a 3D PIC simulation, where we see that at the most front we have proton, which is by green. Then we have a carbon 6 plus, which is by blue. And then we have the heaviest element, which is oxygen, by the violet. Now, because of this multiple charged species, there's an enormous amount of Coulomb explosion, Coulomb repulsion happening at the front of these intersections. And on the left-hand side, we have the numerically simulated spectra of those species. So here we can clearly see that the proton, which is the black curve, is modulated because of the carbon, which is the red curve. And carbon red curve is also modulated because of the oxygen, which is the blue. So we can say in a way that carbon 6 plus is actually pushing or modulating the hydrogen front, and much more heavier oxygen is actually pushing the carbon to get modulated. And this is something we see very clearly in our experiments, that if there is a multi-species involved in the plasma expansion, there is definitely going to happen some modulations in the spectra of this species. And it is very definite. We can predict exactly where the modulation is going to happen by just noticing the maximum velocity of the higher species ions. So let me go to the last section. This is about laminarity of the laser-driven proton beam. Now, why it is interesting is that proton beams are very essential for probing high-dense plasma, because they can go deep in the dense plasma, unlike the optical light field. But before we use them as a probe, we should know the features of this probe, namely their resolutions, their laminarities, and the beam characteristics. So to quantify these parameters, we did a laminarity test experiment with proton beam. And the basic setup is shown here in the top figure here. So we are essentially irradiating laser with a thick target, which is like 6 micron aluminum foil. And because of this interaction, we will have proton beam coming out from the rear side. And we can actually break this proton beam into multiple pixels, like beamlets, by putting a very thick mesh. It's a periodic mesh that we can insert in the path of the beam. So by putting a mesh, we can actually break the entire beam structure into small pixels. And we can see the magnified image of this mesh by putting a plane detector like RCF, a radiochromic film. And so on the bottom, we have image of the proton beam at different energies. For example, 7 MeV, 6, 5, and 4 MeV. And the beauty of these pictures is that all of the pictures are very sharp. That means the quality of the image is very good, or the resolution of the proton beam is very high. And when we take the line out across this grid, we see that the period is very uniform. That means the beam front is highly laminar across all the beam projection. Now, if we can do a simple ray tracing, that means we can reconstruct back how the proton source was at the origin by simply geometrical retracing these beamlets. So when we did this ray tracing, actually we found that all the proton source converges to a very small point, which is known as virtual source. And this virtual source is order of few micron. So that tells us the quality of resolution we have in this proton beam. And we also carried out traditional paper pot emittance measurements, where we found that the emittance of this proton beam is roughly 0.155 millimeter millirad, which is very much similar to what has been reported earlier. So it tells us that the proton beam that we have, it has very good emittance, and it also has very small virtual source, indicating the resolution is very good. That is why our pictures are very sharp. But everything is not so perfect when we looked actually at the lower energy side. So anything beyond 4 MeV or 3 MeV was very much laminar. There was no questions on the sharpness and everything. But when we looked much lower energy, like 2 MeV and 1 MeV, we see that the mesh picture is highly distorted. So unlike the high energy patterns, the low energy patterns are very much distorted with a circular symmetry. This is very well known in optics, which is known as pincushion effect. So this is a distortion created by the proton beam itself. This indicates that our low energy protons are not as good as the high energy part. Now to understand this phenomena, we did once again the ray tracing like we did before, and we found out that this distortion is actually coming from the wings of the lasers. So what we are showing here is like a Gaussian profile of the laser field. So at the central part, we have very high energy protons, and which can be focused down to a virtual point. But the low energy protons, which can also come from the wings, they are not laminar at all. They all belongs to different planes and have a very wide virtual point. So that is the reason that the low energy protons, which are essentially coming from the wings of the laser, are very different in characteristics when we compare the high energy part, which essentially come from the central part of the focus. So this is something that we have to keep in mind when we are trying to extrapolate these results to much higher energies in future probing by the proton beam. So with this, I would like to summarize the talk. So the first section that we saw was about a back reflection issue, which is very fundamental when we irradiate a thin foil with the laser pulse. This essentially comes because of the modulated electron density profile created by the laser. The second thing that we saw was about calibrating our detectors, getting them ready for very high energetic particles that are supposed to be arrived with the next generation of lasers. And as of now, we see that the response is actually getting saturated to a lower level, but it would be interesting to see how it would be in truly transparency regime, like more than 50 MeV or 100 MeV protons. The next thing that we saw was about getting a scaling of ion accelerations and how fast we can accelerate or scale up this proton energy as a function of laser intensity. So at this moment, the maximum energy that we got is like 35 or 30 MeV, but it would be interesting to see what it would take to go to 100 MeV. So that is for the future explorations. Other topic that we saw was about modulating an ion spectrum that essentially comes because of multi-species involved in the plasma expansion, and because of simply Coulomb repulsions, we can modulate and we can predict where the modulations is going to be. And finally, we characterize the laminarity of the proton source towards their applications for the probing of high density plasmas. And we found that the high energy protons are very much laminar, but we have to think about the low energy protons which can come from the wings of the laser. So with this, I would like to thank for your presence and would be happy to take some questions. Thanks a lot.
Thank you, Dr. Prashant, for giving us an overview of a few of your very exciting experiments at the highest of intensities. Now the talk is open for discussion. If you have any questions.
Yes.
You talked about the decrease of the response of the detector at higher proton energy.
Yes.
That is the case with MCP, isn't it?
That is with MCP. Yes.
What about CR39?
CR39, we actually use 1 millimeter thickness. So if we use 1 millimeter thick detector, it is also transparent for 10 MeV proton. But there we can actually use multiple stack, or we can use even thicker one.
No, if that is the case, then wherever you have CR39, you should get proton trace behind CR39 in MCP also, isn't it? But your MCP clearly shows breaks.
Yes. So that is very interesting question actually. So let me show you one of the, because this one I didn't show you for the entire energy, but there is one data where we actually see a transparency. So I'm glad that you asked this question. So let me just very quickly open that transparency data for you. So can you see the slide here? Do you see this slide, or should I zoom it further?
Can you zoom your slide?
Yeah, just one second. Let me zoom into that area. So if you see the yellow part, yellow arrow, this is actually the transparent proton beam which is scattered. So unlike the low energy part, which comes like a beam, pencil beam, this part is actually transparent and it is seen on MCP also. And this is very clearly shown in the inset here. So if we go beyond 10 MeV, we do see that protons are imprinted both on CR39 and also on MCP. So you are absolutely right here. They can be seen on both.
Next question.
Yes.
You said that we are getting modulated spectra due to multispecies.
Yes.
Since you are working at an intensity which is about 10 to the power 21, don't you think it is RPA, which is giving sort of a hump in the energy spectrum?
Yeah. So, yeah, that's a very nice question actually. So to confirm this, we actually did experiments at oblique incidence, and all these measurements that we are showing you is target normal. So if it is RPA, we should have seen something along the laser axis. And in the entire campaign that we have, we don't see any trace of ion acceleration happening towards the laser axis. It's all about TNSA.
But did you try with a circularly polarized beam? Because that will clearly define your RPA and other region.
So for circular, actually, we didn't see any difference at all when we used with the thick foils, 6 micron thick foils. But maybe we should try very thin foils, like few nanometers, and there we should see this.
Thanks.
Yeah, thanks a lot.
Prashant, yeah, my question was very similar to the previous one. So I do think it does look like an RPA spectrum. So you haven't done anything with less than 10 nanometer targets, right?
The maximum we could shoot was like 10 nanometer, but that was close to 0 degree. So there we cannot distinguish between TNSA and RPA.
If with circular you can, with circular polarization you can.
Yes, but what we see is actually the imprint is coming both with the linear and also with circular.
Okay. Do you have you looked for self-transparency?
This we have not.
Okay. Because at these intensities, we have seen that you actually see signatures of relativistic self-transparency as well.
Yes, it is bound to happen because
have a look at Paul McKenna's recent papers.
Yeah, the nature communication.
Yeah. One last question. That's about your first results about the back reflection.
Yes.
Did you see these things with plasma mirrors?
With plasma mirror, actually, we were surprised that it goes up.
It goes up.
More back yeah, we see more back reflection.
So it's not Brillouin scattering or anything like that, which is conjugate.
It's not. Yeah,
okay.
Yeah, it's not that. Yeah.
Okay.
Yeah.
All right.
And we also check the spectra, because if it is SPS, we should see some signature of SPS happening there. But the spectra looks exactly that of the laser itself.
As you said that with plasma mirror, you have more back reflection. Did you see the harmonics also in that?
No, in our diagnostics, it was only the fundamental. So we were looking mostly for fundamental. Yeah.
Because in such a case, you have a plasma mirror which is oscillating at the laser frequency, so it will generate a lot of harmonics. That is well known.
Yes. But harmonics coming in the back reflection direction is specular. Obviously, there is more. But in the back reflection, I was not sure whether we can see. And there's one more thing, that our mirrors are dielectric mirrors. So if it is second harmonic, there's no way we could see in the back like tens of mirrors away. So it will only see the fundamental.
Any more questions? If there are none, let's thank the speaker again. Thank you.